Before, we have worked with the Euler or elastic buckling mode in only one really particular context, and that is the pin-pin situation, meaning the ends of the member are pinned. Now, the other thing that we haven't really talked about is, well, what happens if there is some sort of bracing point for the compression member somewhere along its length? And we're going to address and handle all of that. Right? But the basic model here is that the Euler model, buckling model, is pi squared EI over some sort of length squared. And with basic geometry definitions here, pi squared EI, that can become pi squared EA with the radius of gyration included, r squared times a, which we like to conveniently put down here in the denominator of the denominator, length over r. That becomes a slenderness ratio. And it helps us to understand what the critical things are. It's not about the length itself, it's about how skinny the member is, this sort of characteristic with r in comparison to its unbraced length is a critical value. The A can come over here and we get just a stress value, so it's going to all be about how slenderness the member is and what the stiffness of the material is. Those are those critical factors. Now, a more generalized model to reflect that we don't always have pin-pin conditions is this model where we put this big capital K down here, and this is going to turn this into what we call the effective slenderness ratio. We're going to get into all kinds of details about this. K is called the effective length factor. This is KL over R is the effective slenderness ratio. Something to keep in mind from a big picture standpoint, maybe two things here. One, that what we're working with here is about elastic buckling, and not all columns are going to be sensitive to the elastic aspect of buckling. So that's a real world difference that's we have to, at some point, take account of. And you'll do that in the design courses for different kinds of materials. The other thing, big picture, to realize is that with more sophisticated computer programming, this concept of effective length and the effective slenderness ratio from a numerical standpoint is handled in a different kind of way. But this key concept of thinking about what this effective aspect is still pertinent and valuable in trying to understand and predict what's going to be the result of a more advanced and sophisticated computer model. Right? So let's take a look here specifically at content that's included for us in the design specification for structural steel buildings. It's a very helpful model that's been around for many decades, and although it is changing in how we set it up in the design code, the basic understanding is a really good one, right? And it's this effective length factor kind of model that we're using here. The capital K is the effective length factor, and what it's going to do for us is ultimately get us to find the effective half sine wave buckled shape. So let's go and talk about that again real briefly, right? Here's a case where we have in this fourth one over is a pin-pin member. That's how we derived this Euler model to begin with. And at the instant of buckling, right, we had a perfectly straight member. In that instant of the buckling, we got this half sine wave that showed up. And so that's why you see that half sine wave, which is over the physical length of the member, we have a K value that is theoretically derived to be exactly 1. Right? Now, go to another case, such as what you see here in the one right next door to it. Right? So it's fixed at the bottom. It is pinned to the top, but with the potential that the top of the column can move left or right. And what you see here is a quarter sine wave, and the rest of that half sine wave would be just a reflection of this one. So it would be twice as long, and that's why that K value is 2 times. So this effective length factor turns into an effective length with K times L, right? And so that's why I'm kind of playing around with this whole little notion that you see here. Same thing is true of this last one here, that you have a pin at the bottom now fixed at the top, no rotation, but you do have a sway. So that is, again, a quarter of a sine wave. The half sine wave would be over effectively twice this length, hence the factor of 2 for that one theoretically. Come over to this one, and that quarter sine wave now shows up over only half of the physical length. So if you were to take that and reflect it down, you get a physical length that would be theoretically the same as though it were this whole physical length. This one, oh, wait a minute, what's going on here? Well, that's an inflection point, right? Transition between curvature. And if we go look, that's what we really do in the theory, is we go look to find out where is the inflection point located. And theoretically, when we have pinned at the top, no sway, fixed at the bottom, no sway, then that length turns out to be 0.7 times that physical end-to-end length. So hence K is 0.7. We come into this one that has fixed with no sway on either side, and that equivalent half sine wavelength is 0.5 L, or the K value is 0.5. So that's what's going on there. Now, in real practice, what you do is you take these are theory, and you adjust them for a design value to reflect that you're not going to have any of these idealized conditions in your real structure, but you'll learn about that in your actual design class. We'll stay with the theory for now. Right? So let's recap this. The slenderness ratio is L over R, that unbraced length divided by that radius of gyration. And then we will look at the effective slenderness ratio by taking the effective length and dividing by the slenderness ratio. And when we the radius of gyration. And then ultimately what that means is when we go look at this critical elastic buckling load, then that will be pi squared EA over the square of the effective slenderness ratio. Right? And let's go and apply this in an example.